Hello everyone. Let's continue our discussion on support vector machines. Specifically, we want to discuss nonlinear SVM classification. So we have studied linear SVM classifier. Essentially, we are trying to figure out the street as wide as possible. And for nonlinear SVM classification, what we are trying to deal with, as the name indicates, the decision boundary would be nonlinear. Let's start with this example. So for example, what you saw on the left-hand side is just one dimensional space, which is x1. And then you're trying to differentiate the square, blue square, with the green triangle. You are not able to come back with a separator to see how you are now able to come back with a linear separator to separate the green triangle and blue square. However, what you can do is you add more features to the original dataset to make the dataset to be linearly separable. In this case, if you look at what's on the right-hand side, so not only on x1 dimension, but also on x2 dimension. So in the first, on the left-hand side, it's only on x1 dimension, but on the right-hand side, you introduced one more feature, which is x2. With the help of x2, apparently you see that you can come back with this red dotted, red dashed line to differentiate the blue square with the green triangle. Adding more features help your data to be linearly separable. We can leverage polynomial feature transformation in nonlinear SVM classification case. The way that you do is you have a polynomial features with the specific polynomial degrees, and then you run linear SVC on top of that. In this case, it's a linear SVM classifier using polynomial features. As a result, the decision boundary turns out to be nonlinear. Another thing that you could leverage is something called kernel. Let's pay attention to what is a kernel. Kernel trick is something to make it possible to get the same result as if you had added many polynomial features, even with high degree polynomials, without actually having to add them. How convenient that would be. Essentially telling us that you don't need to do a lot of transformation. You could leverage that kernel method directly so that you can already leverage what the polynomial features can help you in terms of coming back with good classification. Right, if you look at the way that you achieve this, you just need to add this kernel equal to poly. In this case, there are a couple of parameters. One of them is called degree, the polynomial degrees that you need to pay attention, right? And also the second one is coefficient 0. This only tries to determine how much the model is influenced by high degree polynomials versus low degree polynomials. The higher it actually have giving more weights to the high degree polynomials if this coefficient 0 is higher. And C is the one that is we actually know in linear SVM classifier, which controls whether margin violation would be allowed. The larger this number C, then your street would be narrower and less violation would be allowed. Again, here we actually have this discussion one more time. Just want you to be aware, if you compare those two graphs, what's the difference? Difference is, the first one is polynomial degree is 3, second one is polynomial degree is 10, and R is 100, so you actually play more weights to the higher degree polynomials, and with the same C for both of them. As a result, you can see the second decision boundary is actually more curved compared to the first one. And also as a result, the model actually is able to differentiate those two classes slightly better on the right-hand side. Here we want to introduce you to this similarity features. So essentially, idea is if this is in one-dimensional space, assuming that any point can be generated by multiple normal distribution. In that case, if you want to come back with transform this to higher dimensional space, to a two-dimensional space in this particular case, right? We want to regenerate, assuming that this point is actually generated by two normal distribution. Then let's see, for this point, particular point, -1, what happens is it has a distance to this point of 1, and then it has a distance to the other point on the right-hand side of 2 units, right? So we say that it is located at a distance of 1 from the first landmark and 2 from the second landmark. And then if you want to generate a new feature, we can leverage something called Gaussian RBF, Gaussian readout basis function, which takes this function form, exponential of negative gamma distance between x and L, essentially landmark, right? This observation and the landmark, we know one of them is 1, the other one is 2. That distance, right? So once you have this, if you have specific gamma, in this case we have a gamma of 0.3, we can use exponential of -0.3 times 1 squared, because the distance is 1. And for the other one, the distance is 2, so that is 2 squared. And then those generate two new observations. One of them, x2 is 0.74, x3 is 0.3. So essentially, we generated in this two-dimensional space, x2 versus x3, you have new observation that is x 0.74 and 0.3. If you do that for all the points on this line, x1 space, you are able to come back with in this two-dimensional space, come back with all kinds of this type of observations. Now it becomes linearly separable with this dashed line. That's the introduction that we just discussed earlier for SVM, nonlinear regression. You want to map it to a higher dimensional space by adding more features to your data. Okay, this is Gaussian RBF. In order to make it work, you could use the same kernel trick in SVC, and kernel would be going to be RBF, and you can specify a gamma and a C in Gaussian RBF kernel. And then just pay attention that if your model is overfitting, you want to reduce gamma. And if it's underfitting, you can increase it, which is very similar to the hyperparameter C. So when C is really large, you tend to make the road narrower, street narrower, and to reduce the overfitting problem. Let's look at this example to compare all different values of gamma and C. So first of all, let's look at compare those two. For the same C, when gamma is higher, what happens is you can have very curved boundary to figure out the difference between those two classes. Compared to when gamma is small, it's really just a linear line. So you can see that when gamma is bigger, you're actually running the risk of overfitting. In that case, if it's overfitting, you want to reduce gamma for the same level of C. How about compare those two? For the same gamma, when C is larger, it's much more curved boundary, so that it's running the risk of overfitting. You want to reduce that C, not necessarily all the way to 0.001, but by reducing this C equal to 1000, there's chance that you can avoid overfitting. Same thing by comparing to those two charts as well. This is Gaussian IBF kernel. So what exactly does this kernel SVM is doing, right? So we actually didn't spend a lot of time on this dual problem or quadratic programming problem. That's why we want to just give you a flavor of understanding of it. It says you don't really need to transform the training instances at all. Just replace the dot product by its square. Just by doing that, you're able to, the result will be strictly the same as if you had gone through the trouble of transforming the training set, then fitting a linear SVM algorithm. But this trick makes the whole process much more computationally efficient. That's the whole idea of the kernel trick. So you can leverage a linear kernel, you could leverage some other kernels as well. Here are common kernels that you could leverage: linear kernel, polynomial kernel, or Gaussian IBF kernel. Even have a sigmoid kernel that you can leverage in SVM. That helps you to build nonlinear SVM classifier. Of course, these are the continued output or results coming from how you can make predictions with a kernelized SVM, or you can use a kernel trick to compute the bias term. Very interesting point here. If you're starting to get a headache, it's pretty normal. It's an unfortunate side effect of the kernel trick. Okay. In terms of computational complexity, let's compare linear SVC, SGD classifier, and SVC. M is the training instances, and N is the number of features. Just specifically, one thing you should be aware on this table that only SVC actually supports kernel trick. So in other words, if you want to develop a nonlinear support vector machine classifier, it has to be SVC based. And then also pay attention that all of these three different methodologies you could leverage scaling, because scaling helps SVM converge faster. That's pretty much everything. And this concludes our discussion of nonlinear SVM classifier. Thank you.